The Sun. It is the ultimate source of virtually all the energy on Earth. It's the dynamo that drives the weather, and its energy, fixed in simple sugars by photosynthesis, directly or indirectly fuels almost every living thing on our planet. Furthermore, practically all the energy we use to sustain our complex society has its origins in the sun's rays hitting the Earth's surface. Because of its fundamental importance to our existence, the Sun is a critically important subject for scientific study. Solar Orbiter, an ESA mission, in collaboration with NASA, has the objective of sending a spacecraft to monitor and observe the Sun, using a suite of advanced scientific instruments, and at a proximity never before achieved. Scientists hope to learn more about our home star, and in doing so, usher in the next era in solar science. After separation from the American Atlas launch vehicle, the Solar Orbiter spacecraft will travel along a highly inclined escape trajectory on course for the planet Venus. During the few months between Earth and Venus, the Solar Orbiter spacecraft will deploy and check out the instruments and subsystems required to complete the mission successfully. The main elements of the spacecraft are as follows: a heat shield to protect the spacecraft body during close approach to the Sun, a chemical propulsion system to provide orbital and attitude control, a pair of solar arrays to provide power, and a high-gain antenna to allow communication with Earth during the mission. The scientific payload can be divided into two separate but complementary groups: remote sensing instruments, which look through the heat shield to image the Sun, and in situ instruments, which perform measurements in the immediate location of the spacecraft. A deployable boom carries several of the in situ instruments that require a magnetically and electrically clean environment or wide fields of view. Upon arrival at Venus, Solar Orbiter will perform the first in a series of slingshot, gravity-assisted maneuvers, which allow the spacecraft to travel to the final operational orbit using much less propellant than would otherwise be needed. Solar Orbiter will perform several such maneuvers during the 3.5-year transfer phase of the mission. Each one is designed to alter the trajectory of the spacecraft to target the next planet in the sequence, gradually reducing the orbital energy of the spacecraft and bringing it closer and closer to the Sun. After the first swing-by at Venus, the spacecraft will return to perform 2 swing-bys around the Earth, which will increase the inclination at escape velocity beyond that which is possible using a direct launch. After the second gravity-assisted maneuver at Earth, the spacecraft will again be bound for Venus, and it's at this second swing-by around Venus that the spacecraft will enter the operational orbit around the Sun. The spacecraft's operational orbit brings Solar Orbiter to around a quarter of the distance of the Earth from the Sun. The spacecraft will rendezvous with Venus every third orbit, and at this point the spacecraft will again perform a gravity-assisted maneuver to increase its orbital inclination. This maneuver will be repeated over the course of the mission, allowing access to the higher latitude regions of the Sun. During the operational orbit, the in situ instrumentation will be permanently active. However, the remote sensing instrumentation will only operate during 3 distinct science windows per orbit, which will coincide with the points of minimum and maximum heliolatitude and the point of closest approach. Of particular interest is the science window at the point of closest approach, which effectively provides a co-rotating vantage point where the angular velocity of the orbit approaches the angular velocity of the Sun, allowing continuous observations of the same regions of the solar surface for extended periods. At its closest approach to the Sun, Solar Orbiter will encounter almost 13 times the solar flux received at the Earth, necessitating the presence of the heat shield on the spacecraft. The heat shield is conductively isolated from the rest of the spacecraft using discrete mounting blades, and is composed of a separate, highly insulating layer held above a support structure by brackets. Also included are feed-throughs, doors, and mechanisms which provide the required fields of view for the remote sensing instruments. The heat shield relies on being able to reject heat to cold space via the gap between the layers. However, it is not possible to keep every part of the spacecraft behind the heat shield. The solar arrays must be exposed to the Sun, and the high-gain antenna must sit in the sunlight in order to access the widely varying Earth positions. Accordingly, Solar Orbiter must manage the temperature of these critical items to ensure their survival as the distance to the Sun varies. As the distance to the Sun decreases, the solar arrays are progressively tilted in order to reduce the effective area exposed to the Sun, hence limiting their temperature. During close approach to the Sun, the high-gain antenna may need to be folded behind the shadow of the heat shield to protect it from the intense solar flux. During these periods, the spacecraft will be operating autonomously and will still acquire data during science windows. Collected data are stored in onboard memory and then forwarded to the Earth once communication again becomes possible. Solar Orbiter is an advanced mission in the best traditions of European science, using a pragmatic blend of existing and new technologies to achieve the mission's scientific objectives. The vantage point offered by the spacecraft trajectory will be unique, encompassing both near-Sun and high-latitude views, and the combination of remote sensing and in-situ measurements promises to revolutionize our understanding of the Sun.